Hello, my name is Adrian Miranda, and these are my partners, Brett Black and Jaden Colvin. Today we're talking about standard atmosphere, and we are on part C of this project. I'm going to be talking about the original process. The concepts of the standard atmosphere began in the 17th and 18th centuries when scientists tried to understand how air pressure changes with altitude. Early experiments were performed using mercury barometers, which measured atmospheric pressure by the height of the mercury column. One of the most influential figures was Evangelista Torricelli in 1643, who built the first barometer by filling a glass tube with mercury and inverting it into a dish. Later, Blaise Pascal expanded Torricelli's work by measuring air pressure at different heights on a mountain, proving that pressure decreases with elevation. These early measurements helped form the foundation for defining a standard value for atmospheric pressure. Next, I'm talking about the difficulties or complications. Scientists faced several difficulties in those early studies, which include limited technology. They had no precise instruments to measure temperature or altitude, making data inconsistent. Also, the mercury barometers were fragile and unsafe due to mercury's toxicity. Environmental factors such as humidity and temperature variations affected readings. There was also no universal standard, so different countries used different reference pressures and temperatures. The motivation for this was to understand how air pressure behaves and to create a consistent reference for scientific and engineering calculations. The study of atmospheric pressure was crucial for improving weather predictions, designing early air pumps and later aircraft instruments, establishing a baseline for gas loss and fluid dynamics. The original benefits of the discovery were that when scientists first defined the standard atmosphere, it provided a universal reference for physics, chemistry, and engineering, the basis for aviation altimeters and meteorological data, and a better understanding of how pressure, temperatures, and altitude interact in Earth's environment. This discovery unified how scientists and engineers discussed and calculated pressure worldwide. The modern experimental process was that today the standard atmosphere is studied using advanced meteorology instruments and satellite data instead of mercury barometers. Digital barometers and pressure sensors now measure air pressure with high precision using electronic transducers. Weather balloons and radiosones collect data on temperature, humidity, and pressure as they rise through the atmosphere. Satellite monitors atmospheric conditions globally, giving a scientist a complete model of how pressure changes with height and across locations. The differences in modern approach. Modern approaches have improved dramatically, with instruments that are digital, safer, and more accurate, and with no mercury. Data is collected continuously and globally, not just at single points. Computer modeling allows simulations of atmospheric conditions under different climates or planets, and the standard atmosphere is now defined mathematically through international standards that includes variations with altitude, temperature, and density. Modern benefits of the discovery were that the concepts of standard atmosphere now supports aviation and aerospace, weather forecasting and climate models helping predict storms and global warming effects, engineering applications such as air conditioning, combustion systems, and pressure vessel design, and environmental monitoring, ensuring accurate measurements of air quality and greenhouse gases. The future expectations of the research are that they develop more detailed dynamic atmospheric models that include pollution and climate feedback effects. Also, to use AI and satellite constellation to refine real-time global pressure maps. They want to apply atmospheric standards to other planets for space exploration missions, and they also like to improve precision navigation systems by integrating atmospheric correction data into GPS and aerospace technologies. And that is it for our presentation.
Hello, my name is Brett Black, and this is my Part C for my physics class, Standard Atmosphere. Uh, Starting off with the original process, the original lab, was mainly outside. They talk about how the main experiment that they used to find different standard atmospheric pressures was actually one of them climbed a mountain with the mercury barometer and like glass tubes, water columns, just to see the difference. No electricity, no computer, no crazy anything. It was all handmade, very straight to the point. And they tracked how mercury moved. And that's how they did things with the original process. Original difficulties. Obviously they just didn't understand what it was in the beginning, or even that there was a difference in pressure in altitude. So that was definitely one of the biggest hurdles they had to overcome. Also, they hand built their tools to figure this out, so that was definitely something else. Safety issue. Mercury right away. In fact, they made that with their hands. Very simple on how that is a safety issue. And obviously, back then, safety protocols did not exist. Um, Equipment. Things were very simple, handmade, very fragile, not reliable. So many things wrong with it, but they were able to see the difference in their experiment. Um, processing information and collecting data, same thing. They just took notes, used their eyes, used their best judgment, and were able to see that there was a difference. Motivation, obviously was to understand how pressures worked and try to figure out whether, and if it was higher pressure at higher altitudes, lower pressure at higher altitudes, just trying to figure that out. Benefit a lot of people, benefit scientists, engineers, inventors, the general math public, um, just by helping understand our atmosphere. Original benefits, they were able to figure out the beginnings of weather patterns and why liquids sometimes rose in tubes and how gases behaved under different conditions. There's a lot of um, intermediate advancements in like other fields, like obviously engineering. It helped improve pumps, hydraulic systems, and early machinery. And with standard different conditions, you're going to have higher and lower fluids, higher pressures, lower pressures, so on and so forth, which created a lot of brand new fields: meteorology to understand weather, aviation for flying, performance calculations, and space exploration, and so on and so forth. The modern process is so much more different. We have all these tools. We have radar. We have brand new equipment to recognize the pressure. Altimeters, barometers, automated weather stations, so much. Computer software, so much. And experimental procedures. It is pretty straightforward. Start off. They just collect data off the past and keep going and keep going, and they use this data to get better understanding of different pressures. Modern differences, modern advancements. Kind of the same thing, just using new technology, satellites, sensors, tools, equipment to better understand it. We've just been understanding it more and more the further we've been going on. Safety, obviously OSHA, protective gear, glasses, gloves, whatever you need for the experiment is there. It's readily accessible. Information gathering is huge, huge difference. All those tools that we use now, and then it's all put into computer software where it collects it, analyzes it, and you can track it through the years. To the digit too. Very straightforward. Modern benefits. engineers are able to understand it so much more. Temperature and density for meteorology, forecasting for aviation safety. And there's a whole breakdown of aviation safety depending on the weather, climate research for the better environment of Earth. Um, and a lot of scientific fields benefit from that from now on. Future expectations, I think, I feel like we can get meteorology down to 100%. I mean, it is a guesswork. I mean, every time you check the weather, it's very different. But I feel like we can get it down to 100% the more and more we collect data and understand it. And that's it. Thank you so much.